Hi, guys. Welcome back to our ongoing discussion about biochemistry and biophysics. Um, Today, we're going to push on past the subjects we've been talking about in terms of protein structure and protein folding and protein stability. And we're going to start taking some of those ideas for granted and utilizing them to start looking at aspects of protein function. But before we do that, we need to spend a little time talking about some essential tools that are at the core of the toolbox that we use as biochemists or biophysicists, right? So if you think about those two papers we just read, right, and the last paper discussion, the conclusions in those papers are based in whole or in part on a particular kind of approach, right? If you think about that, right? Um, Specifically, that approach was spectroscopy, right? Light scattering, circular dichroism, NMR spectroscopy, right? These are all tools based upon studying properties of matter um, through their interactions with electromagnetic radiation, right? And if you think back to maybe other papers you've read or maybe other things you've seen, um, there are incredibly varied sets of tools for studying fundamental mechanisms and properties of how things work in the natural world using tools that are based around spectroscopy, right? For example, the ways in which you can study protein folding that are based in spectroscopy, right? The simple absorption of light, as I've mentioned to you, absorption of light by um, the aromatic residues and how that changes as a function of protein state. Fluorescence, right, which is an emission of light following an absorption event of light, is an incredibly sensitive tool across a wide variety of domains for studying aspects of protein structure and dynamics and function. Circular dichroism, which we've talked about, right, gives you information about secondary structure content. And even NMR, right, when you get down to it, NMR is operating in a different way. It's not looking at electronic structure, it's considering nuclear structure of molecules. Um, and but it is still fundamentally a property based in the interaction of matter with electromagnetic radiation, right? So, and this is not just for protein folding or even for biochemistry, right? Across just a huge range of domains in the sciences and in engineering. If we didn't have these tools built around spectroscopy, we couldn't do a lot of what we do, and we couldn't understand a lot of the things we need to understand about how the world works. Um, so what is spectroscopy definitionally, right? Well, fundamentally, spectroscopy, of course, is simply is a large family or an ever-growing family of measurement techniques that are built around, like I said, the interactions of light with matter, right? Sort of my title here, right? Um, and like I said, it's an essential tool. Without this, we would have very, very few ways of probing a lot of fundamental aspects of um, material in the world, from the biological sciences to chemistry to the physical sciences. Um, and the roots of spectroscopy, as we think about it as a quantitative science, really sort of can trace its origins back to roughly 16th century Europe, where the beginnings of the quantitative sciences of spectroscopy really had their start. But the idea of really something interesting and really fundamentally remarkable going on as light interacted with matter has much deeper origins than that, going back to ancient China, ancient Greece, and Egypt even. Um, so in addition to this fundamentally important tool that we really need to understand, so that we're not just like using a black box, light also biologically is critically important, right? Think back to that example I gave you guys at the beginning, um, of where most all the energy in the natural world comes from. It comes from the sun, which means it comes from plants running a photosynthetic process that captures radiant energy, light, and turns it into chemical energy, right? You think about vision, right? Your ability to see me right now depends upon the interaction of light with a particular type of cells in the retina of your eye. Sunscreen, if you want an applied example. I mean, the list just goes on and on, right? So in addition to just the practical and utilitarian aspects of understanding the interaction of light with matter as a tool, there's all these biologically important aspects of the process as well. So we really kind of want to understand that, right? At least at sort of a basic working level. So reasonable place to start then is just to back up and say, well, what is light, right? And you guys hopefully all remember this from your basic high school physics, that light is, of course, this oscillating electromagnetic wave with orthogonal electric field and magnetic field components that oscillate in space. And the light of a given energy will have a particular frequency. It will also, which would be the number of times it oscillates as a function of time. It will also have a given wavelength, the separation between the peaks of the electric field or the magnetic field component. We're going to have a fixed spatial length as a function of particular energy of the light, right? Another interesting thing about this diagram that I'm showing here is that you notice that down this propagation direction, down this x-axis here, that the electric field basically stays oriented, right? It's following sort of a plane. This is an example of plane polarized light. In which the electric field vector doesn't change its spatial orientation down the direction of propagation, but that doesn't have to be true, right? In fact, in circular dichroism spectroscopy, what you're looking at is light that is so-called circularly polarized, in which case that electric field vector, in addition to oscillating in magnitude, sweeps spatially around the propagation axis, so that you have sort of a corkscrew of the electric field oscillating in intensity and then orientation. Okay, so those are those some of the basic little properties of light, and then of course we know that the quantitative description of this process of this phenomenon, electromagnetism, was supplied by the great Scottish physicist by the name of James Clerk Maxwell in the mid-19th century. Maxwell derived the first set of complete equations that describe the wave behavior of phenomena like electromagnetic radiation. He showed that the electric field magnitude and a beam of light, of course, oscillates in a characteristic way, simple sort of cosine function related to the peak magnitude of that electric field vector, and then the cosine of a function related to the frequency, right, and the wavelength of light, which are then, of course, connected by the speed of light, right? And this was sort of in the mid 19th century when Maxwell sort of built this beautiful edifice of electromagnetism, seemed to settle an old debate that went all the way back to at least Newton in terms of what was the fundamental nature of light. And there had been a debate raging for centuries about whether it was a wave phenomenon or something that was more particulate, like it was called the corpuscular theory of light. And with Maxwell's incredible work, it seemed like this problem was resoundingly decided on the side of light was a wave phenomenon. And then not 40 years, 30 some odd years later, along came the great German physicist by the name of Max Planck, who was studying blackbody radiation. And he realized that you could not quantitatively explain the behavior of the frequency distribution of blackbody radiation using Maxwell's wave description of light. He realized that it just wasn't possible. And the only way to physically explain it was to postulate the existence of discrete packets of energy, which we now know, of course, as photons, that Maxwell showed were quite simply the energy of those photons was simply related to the frequency of the light and a constant we now know as the Planck constant, right? That's 6.6 times 10 to the minus 34 joules seconds, all right? Okay, so this sort of recapitulates, hopefully, stuff you guys remember, that the sort of well established, if not completely intuitive idea of the wave-particle duality of electromagnetic phenomena like light, right? That they can, under some circumstances, behave beautifully like waves, and other circumstances, much more like particles, photons, and that to really explain phenomenon of light, the phenomenon of light, you kind of have to incorporate the idea that electromagnetic phenomena like this sort of had characteristics of both, right? Okay, so with that little sort of review about what is light, what happens when light interacts with matter, right? And all kinds of interesting things can happen when light interacts with matter, right? If the index of refraction of the material is of a particular difference with the transmitting medium, and if the angle is right, and if the reflectivity of that surface is right, that incident light radiation can just be completely reflected back off with no change in energy whatsoever. The polarization, depending on how you do it, can change, right? But it can just bounce right off, right? Or the light, of course, can be transmitted, right? And again, if the index of refraction of the transmitting medium is different from the incident medium, the wave velocity of the light transiting that substances will change, will slow, and the light beam will bend or refract, right? So you guys hopefully remember that. Depending upon the type of the intervening medium, all right, the light transmitting can actually scatter. It can interact with elements in the transmitting medium, and not simply reflect, but scatter off. And there are a couple of different ways in which the scattering can happen. It can happen with no loss of energy, which is known as Rayleigh scattering, or if there is a partial transfer of energy in a really fascinating process known as Raman scattering. If you want to know more about that, I would go seek out and talk to Dr. Kurowski. This is a particular type of spectroscopy he specializes in, and it's a very powerful tool for looking at molecular structure and bond oscillation frequencies. But the kind of process, we're not going to really talk about any of those. The process we're going to be fundamentally interested in is this one here. When the light sort of transmits and goes in and stops, basically, the energy is absorbed completely into the medium, right? And it's this process of absorption that we're pretty much going to be focusing our attention on, right? When the energy of the incident light is mostly or substantially directly absorbed by the intervening medium, right? Now, there are a couple of ways one can think about this process. And so here again is a set of those reference spectra I showed you before for the absorption of ultraviolet light down here with the aromatic residues of a protein, right? And there are, at least two different ways, fundamental ways one can think about understanding this process. One is fundamentally a descriptive explanation, one that basically describes what happens and even quite quantitatively describes what happens. The other is a mechanistic explanation, the sort of why of the absorption of light by the matter, right? Or by aromatic amino acids. Both are correct, but one, the mechanistic explanation, gives you insight that the descriptive mechanism explanation doesn't necessarily. However, in this case, this descriptive explanation is fantastically practically useful. And the reason it's practically useful is because it lets you answer questions like this. If I had a protein and I know it absorbs light in UV, I can use this descriptive explanation of absorption to specify with precision how much I have. So the absorption spectroscopy, which you will use as a common tool if you remain doing wet bench biochemistry, it's like a go-to utilitarian tool, is incredibly important, right? And so that's where we're going to start in our description of the interaction of light with matter.